Dear students, we already know that we cannot exactly measure the momentum and position of an electron. That means we fail. Our classical theories fail in the microscopic level. And now we are discussing the quantum mechanics or the behavior of microscopic particles. In 1900, Max Planck introduced the concept of quantum energy. നമ്മൾ ഇതിന്റെ ജസ്റ്റ് ഈ ഫസ്റ്റ് ചാപ്റ്ററിൽ ഞാൻ ജെറ്റ്ലിന്റെ ബുക്കാണ് ഫോളോ ചെയ്യുന്നത്. ഫസ്റ്റ് ചാപ്റ്ററിൽ പറഞ്ഞിട്ടുള്ള കുറച്ച് പോയിന്റ്സ് മാത്രം നമുക്ക് നോട്ട് ചെയ്ത് പോവാം. 1905, Einstein provided a powerful consolidation to Planck quantum concept in trying to understand the photoelectric effect. Photoelectric effect എന്താണെന്ന് നിങ്ങൾക്ക് അറിയാം അല്ലേ? Scattering of the electron from the metal surface when a high energy photon incident on the metal surface. Already പഠിച്ചു കഴിഞ്ഞിട്ടുണ്ട്, അത് നമ്മളിവിടെ ഡിസ്കസ് ചെയ്യാൻ പോകുന്നില്ല. And in 1911, Rutherford experimental discovery of the atomic nucleus. Then in 1930, ഇതിന്റെ historical quantum mechanics history എങ്ങനെയാണെന്നാണ് നമ്മൾ ഡിസ്കസ് ചെയ്യുന്നത് കേട്ടോ. സോ കുറച്ച് പോയിന്റ്സ് മാത്രം. 1913, Bohr introduced his model of hydrogen atom. ഈ വർഷങ്ങൾ ഇങ്ങനെ നോക്കുക കേട്ടോ. 1900 മാക്സ് പ്ലാങ്ക് ഇൻട്രൊഡ്യൂസ്ഡ് ദി ക്വാണ്ടം എനർജി. 1905 ഫോട്ടോ ഇലക്ട്രിക് എഫക്റ്റ്. 1911 Rutherford experimental discovery of the atomic nucleus. In 1913 Bohr model of hydrogen atom. In 1923 Compton made an important discovery that gave the most conclusive confirmation for the corpuscular aspect of light. By scattering X-rays with electrons, he confirmed that the X-ray photons behave like particles with momenta h nu by c. In 1923, they believed that the photons are particles or the light of particles. Planck, Einstein, Bohr and Compton gave both the theoretical foundations as well as the conclusive experimental confirmation for the particle aspect of wave. That is a concept that waves exhibit particle behavior at the microscopic scale. At this scale, classical physics fail not only quantitatively but even qualitatively and conceptually. In 1923, the Broglie introduced wave nature of the particles. Material particles themselves display wave-like behavior. This concept confirmed experimentally in 1927 by Davison and Germer. They showed that interference patterns, a property of waves, can be obtained with the material particles such as electrons. Davison German experiment എന്താന്നുള്ളത് നമുക്ക് നോക്കാവുന്നതാണ്.
Davison and Germer experiment. In 1924, Louis de Broglie postulated that all forms of matter have both wave and particle characteristics. According to this hypothesis, electron, just like light, have a dual particle wave nature. Two American physicists, C.J. Davison and L.H. Germer, were the first to experimentally prove the wave nature of material particles in 1927. Displayed here is a block diagram of the experimental setup used by Davison and Germer. It consisted of a nickel chloride crystal, the target, an electron gun, G, and a detector. The electron gun produced a beam of electrons. The electron gun used by them consisted of a tungsten filament, F, and high and low tension batteries. The low-tension battery was used to heat the filament. The red-hot filament produced an electron beam. A high-tension battery was provided to accelerate the electron beam. The detector or the electron collector moved on a graduated circular scale. A sensitive galvanometer was also connected to the detector. How did they perform the experiment? The electron beam was made to pass through a pinhole and made to strike the crystal normally. The electrons scattered in all directions, acting like waves. They observed that at certain angles, the detector indicated a peak in the intensity of the scattered electron beam. This maximum intensity was due to constructive interference, a phenomenon confined only to waves. Thus they experimentally proved the wave nature of electrons. Davison and Germer plotted a graph taking the angle between the incident and scattered direction of the electron beam, phi, along the y-axis and the intensity of the scattered beam at different values of accelerated potentials along the x-axis. The nature of the graph is shown here. From the experimental curves obtained, the following conclusions were drawn. Intensity of scattering depends upon the angle of scattering, phi. A bump or kink always occurs in the curve when phi is equal to 50 degrees. This bump or kink increases as the accelerating potential difference is increased. At 54 volts, this bump is maximum and then it decreases on further increase of potential difference. This peak indicated the wave behavior of the electrons. Thus, Davison-Germer experiment verifies de Broglie's hypothesis of wave nature of matter particles.
Introducing Speech-Alone, the most natural sounding.
Davison-Germer experiment നമ്മൾ കണ്ടു that proves the wave nature of the electrons, where we have got the interference patterns. Okay, 1927. Then during that time, Heisenberg and Schrodinger in 1925, they put quantum mechanics. This new theory had put an end to 25 years, 1900 to 1925, where different experiments, the wave nature of particle nature of the light waves, അങ്ങനെ contradictory ആയിട്ടുള്ള different experiments-ഉം theories-ഉം എല്ലാം വന്നു. Then 1925 Heisenberg and Schrodinger put an end, and the history of the quantum mechanics started. There were two independent formulations of quantum mechanics. They introduced two different formulations. The first formulation called the matrix mechanics. ഇതാണ് നമ്മൾ ഇനി നമ്മൾ സിലബസിൽ പഠിക്കുന്നത്. ഇതിന്റെ ഹിസ്റ്ററി അത്ര വലിയ ഇമ്പോർട്ടൻ്റ് അല്ല. എന്നാലും നിങ്ങൾ ഡേവിഡ്സൺ-ജെർമറും സ്റ്റേൺ-ജെർലാക്ക് എക്സ്പെരിമെന്റ് നിങ്ങൾ ഓർത്തിരിക്കുക എന്താണ് എന്നുള്ളത്. Then the matrix mechanics developed by Heisenberg in 1925 to describe atomic structure starting from the observed spectral line. അതിൻ്റെ ഇടയ്ക്ക് നമുക്ക് സ്റ്റേൺ-ജെർലാക്ക് എക്സ്പെരിമെന്റ് കൂടി നമുക്ക് നോക്കാം. എന്താണ് സ്റ്റേൺ-ജെർലാക്ക് എക്സ്പെരിമെന്റ്, അതൊന്ന് എന്താണ് നമ്മൾ കാണുന്നത് നോക്കാം. Stern-Gerlach experiment proved the 1922. It is proved that degrees of freedom of an electron spin or the quantization of spin is
The
proved by
Stern-Gerlach
Stern-Gerlach
experiment,
experiment.
performed in 1922, delivered the first experimental proof of the fascinating degree of freedom of an electron spin. A beam of silver atoms was generated in an atomic beam furnace. It was then sent towards an inhomogeneous magnetic field. According to classical physics, one would expect the magnetic moments of silver atoms to be randomly oriented. They should be deflected in the inhomogeneous magnetic field by different amounts, depending on their orientation. However, the researchers observed that the beam was split in two possible states, which were later named spin up and spin down. How can this be explained? Let us first analyze the electron configuration of a silver atom. One silver atom has a total of 47 electrons. In 46 of these electrons, each spin up is paired with one spin down. The spins neutralize each other. There is only one unpaired spin, the spin of the 5s electron. It can be either in spin up or spin down, or in any superposition of these two states. We can represent this spin state using a Bloch sphere. The spin can point in any random direction. The spins of all silver atoms are randomly distributed. They are therefore not polarized. In fact, there is a close connection between this experiment with a single electron spin and the experiment with single polarized photons. Here, the polarizing filter corresponds to the inhomogeneous magnetic field. Just like with photons, in a single experiment, it is completely random whether the spin points in the direction of the polarizing filter or in the opposite direction. The result is a black and white random pattern. Let's have a closer look at the quantum mechanical measurement process in the Bloch sphere. The spin has some arbitrary orientation before it interacts with the inhomogeneous magnetic field. The inhomogeneous magnetic field acts as a filter. It is presented here as a slot. It forces the spin to take a random orientation, either in line with the inhomogeneous magnetic field or in the opposite direction. If the basis state is close to up, it is very unlikely to change the direction in down. However, it may still do so. When performing their canonical experiment, Stern and Gerlach were unable to use single silver atoms. Therefore, they could not demonstrate the role of chance in each experiment. However, they were the first to demonstrate that the spin is quantized, or separated in up and down. It was a sensational achievement in their time.
നമ്മൾ സ്റ്റേൺ ജെർലാക്ക് എക്സ്പെരിമെന്റിൽ ക്വാണ്ടൈസേഷൻ ഓഫ് സ്പിൻസ് നമ്മൾ കണ്ടു. Then 1925 they have introduced two formulations to study the quantum mechanics, metrics and then expressing dynamical quantities such as energy, position, momentum and angular momentum in terms of metrics. In the metrics mechanics, everything is represented in the matrix form. The diagonalization of the Hamiltonian matrix yields the energy spectrum and the state vector of the system. Matrix mechanics was very successful in accounting for the discrete quanta of light emitted and absorbed by atoms. Then second formulation is wave mechanics. നമ്മൾ ഓൾറെഡി നിങ്ങൾ ലോവർ ക്ലാസ്സിലൊക്കെ പഠിച്ചിട്ടുള്ള wave mechanics due to Schrodinger in 1926. It is a generalization of the de Broglie postulates, which describes the dynamics of microscopic matter by means of wave equation called the Schrodinger equation. Instead of the matrix eigenvalue problem of Heisenberg, Schrödinger obtained a differential equation. അപ്പോൾ നമ്മൾ ഈ പേപ്പറിൽ നമ്മൾ പഠിക്കുന്നത് ഈ രണ്ട് ഡിഫറെൻറ്റ് ഫോർമുലേഷൻസ് ആൻഡ് മറ്റൊരു ഫോർമുലേഷനാണ് Dirac then suggested a more general formulation of quantum mechanics, which deals with abstract objects such as ket vector, and bra vector and operators. The representation of Dirac formalism in a continuous basis, position or momentum representations gives back Schrödinger wave mechanics. As for Heisenberg matrix formulations, it can be obtained by representing Dirac formalisms in a discrete basis. Combining special relativity with quantum mechanics, Dirac derived in 1928 an equation which describes the motion of electrons. This equation, known as Dirac's equation, predicted the existence of an antiparticle, the positron, which has similar properties but opposite charge with the electron. The positron was discovered in 1932. അപ്പോൾ നമുക്ക് സമ്മറൈസ് ചെയ്യാന്നുണ്ടെങ്കിൽ what is the quantum mechanics എന്ന് പറഞ്ഞാൽ quantum mechanics is the theory that describes the dynamics of matter at the microscopic scale. നമുക്ക് അതിൻ്റെ ഒരു തിയറി ഇതുവരെ പറഞ്ഞത് മൊത്തം കാര്യങ്ങൾ വെച്ച് നമുക്കൊരു വീഡിയോ നമുക്ക് കാണാം.
Quantum physics has a mystique of being complicated and hard to understand. In fact, Richard Feynman, who won the Nobel Prize for his work on quantum electrodynamics, said, "If you think you understand quantum physics, you don't understand quantum physics." Which is kind of disheartening for us, because if he didn't understand it, what chance do the rest of us have? Fortunately, this quote is a little misleading. We do in fact understand quantum physics really well. In fact, it's arguably the most successful scientific theory out there, and has let us invent technologies like computers, digital cameras, LED screens, lasers, nuclear power plants. And you don't really want to build a nuclear power plant if you don't really understand how it works. So quantum physics is the part of physics that describes the very smallest things in our universe. Molecules, atoms, subatomic particles, things like that. And things down there don't quite work the same way that we used to up here. This is fascinating because you and everything around you is made from quantum physics. And so this is really how the whole universe is actually working. I've drawn these protons, neutrons and electrons as particles, but in quantum mechanics we really describe everything as waves. By the way, I'm using quantum physics and quantum mechanics interchangeably, they're the same thing. So instead of an electron looking like this, it should look something like this. This is called a wave function. But this wave function isn't a real physical wave like a wave on water or a sound wave. A quantum wave is an abstract mathematical description. To get the real-world properties like position or momentum of an electron, we have to do mathematical operations on this wave function. So for the position, we take the amplitude and square it, which for this wave would look something like this. This gives us a thing called a probability distribution, which tells us that you're more likely to find the electron here than here. And when we actually measure where the electron is, an electron particle pops up somewhere within this area. So with quantum physics, we don't know anything with infinite detail. We can only predict probabilities that things will happen. And it looks like this is a fundamental feature of the universe, which was quite a departure from the clockwork deterministic universe in classical physics, the kind of thing Newton derived. This wave function model predicts what subatomic particles will do incredibly well, but weirdly we've got no idea if this wave function is literally real or not. No one's ever seen a quantum wave because whenever we measure an electron, all we ever see is a point-like electron particle. So there's like this hidden quantum realm where the waves exist, and then the world we can see, which is where all the waves have turned into particles. And the barrier between these is a measurement. We say that a measurement collapses the wave function, but we don't actually have any physics to describe how the wave collapses. This is a gap in our knowledge that we've dubbed the measurement problem, and this is one of the things that Feynman was referring to with his quote. Another confusing thing is how exactly to picture an electron. It seems to be a wave until you measure it, and then it's a particle. So what actually is it? This is known as particle-wave duality, and here's an example of it in action, the famous double-slit experiment. Imagine spraying a paintball gun at a wall with two openings in it. You'd expect to see two columns of paint go through and hit the wall behind. But if you shrink this all down to the size of electrons, you see something quite different. You can fire one electron at a time at the slits, and they appear on the back wall. But as they build up over time, you get a whole pattern of stripes instead of just two bands. This pattern of stripes called an interference pattern, something you only see with waves. The idea is that it's the electron wave that goes through both slits at the same time, and then the waves from each slit overlap with each other. And where the waves add together, you've got a high probability of the electron popping up at the wall, but where the waves cancel out, the probability is very low. So actually on the back wall, the highest probability of finding the electron is in the middle of the slits. And then it goes down, and then up again and down and up again, and this is the interference pattern. So when you fire one electron after another, they follow this probability distribution, and this interference pattern starts building up, and that's exactly what we see in experiments. So this shows that electrons behave like waves in this experiment. The question is, what actually happens to this spread out electron wave when you do a measurement? It seems like it goes from this spread out wave to this localized particle. But like I said, there's nothing in quantum mechanics that tells us how the wave function collapses. And this is not only true for electrons, but everything in the universe. So this double slit experiment has huge consequences for our model of the universe. And it was very surprising the first time it was done. Physicists are still grappling with this question today and have come up with many interpretations of quantum mechanics to try and explain these results, and explain how reality actually works. Okay, let's go back to the wave function. We can now use this picture to explain other features of quantum physics that you may have heard about. So this is just one possible wave function for an electron, but there's many others, like this one for instance. This says that the electron has a probability of being over here and a probability of being over here, and very little probability of being in the middle. This is perfectly allowable in quantum physics, and this is where the phrase "things can be in two places at once" comes from. This is known as superposition, which comes from the fact that this wave can be made by adding, or superimposing, these two waves. The word superposition just means the adding together of waves, and we already saw this in the double slit experiment. And it's not really a very special phenomenon. You can even see superposition by dropping two pebbles into a pond where the ripples overlap. Now for entanglement. Let's say two electron waves meet. Their waves interfere with each other and become mixed up. This means that mathematically we now have one wave function that describes everything about both electrons, and they're inextricably linked, even if they move far away from each other. A measurement on one of the particles, like measuring if it's spin up or down, is now correlated with a measurement on the other, even if they move billions of miles away. Einstein was very uncomfortable with this idea because if you measure one of the particles here, you instantaneously know what the other will be, even if it's billions of miles away. And that's got a sort of whiff of faster-than-light communication, which is not allowed by the theory of relativity. But it turns out you can't actually use this to communicate information, because the measurements give you random results. But the fact that they are correlated means that somehow there is a link that stretches over that distance. This is called non-locality. Quantum tunneling. Quantum tunneling is where particles have a probability of moving through barriers, essentially allowing things like electrons to pass through walls. When a wave function meets a barrier, it decays exponentially inside the barrier. But if the barrier is narrow enough, the wave function will still exist on the other side, meaning that there's a probability of the particle being found there when a measurement is made. In fact, the only reason you're alive is because of quantum tunneling in the sun, which makes the sun shine. Protons normally repel each other, but they've got a small probability of quantum tunneling into each other, which is what turns hydrogen into helium and releases fusion energy. All life exists on Earth because of energy from the sun, except for life around hydrothermal vents. Now onto the Heisenberg uncertainty principle. I said at the beginning that this wave function contains all of the information like position and momentum of the electron. We just have to do some maths on it. The position is given by the amplitude or height of the wave. and the momentum is given by the wavelength of the wave. But for this specific wave, the position gives us a probability distribution, so we don't know exactly where the electron is. Also, there's an uncertainty in the momentum because this wave is made of many different wavelengths. But we can reduce that uncertainty. Let's have a wave that only has one wavelength, so a sine wave. Now we know the momentum exactly because the wavelength has a single value. But look at the position. There's an equal probability of the electron being found anywhere in the universe. Okay, let's do the opposite. Let's make a wave that has only one position. Now we know exactly where the electron is, but what's the wavelength of this wave? Now the wavelength is very uncertain. Basically, only a sine wave gives you a precise momentum. And any wave that isn't a perfect sine wave, you have to build out of multiple different sine waves. And each of those multiple different sine waves has got a different wavelength, and hence you have a range of the possible different values of momentum for the particle. This is Heisenberg's uncertainty principle. You can only know certain things precisely, but not everything. Either you've got a definite value of momentum and don't know anything about position, or you know the position very well, but don't know anything about the momentum. Or you're in some intermediate state. And this isn't a limit of our measuring apparatus, this is a fundamental property of the universe. And finally, where does the name quantum come from? Well, a quanta is a packet of something, like a chunk of something. And one of the first quantum effects people saw were atomic spectra, which is where atoms give off light with specific discrete energies. It works like this. Imagine a string that's tied at both ends, like a guitar string. If you pluck it, only certain waves can exist because the ends are tied down. In this situation, we say that the wavelengths are quantized to certain values. The same thing happens if you tie the ends of the string together because the waves have to match up. They can only vibrate in certain restricted ways. And this is what's happening to an electron in an atom. The electron wave is constrained by the atom and quantized to certain wavelengths. Short wavelengths have got a high energy and long wavelengths have a lower energy. This is why the light emitted by an atom looks like a barcode, because each bar of light corresponds to an electron jumping from a wave with a high energy to one with a lower energy, and, at the same time, emitting a quantized photon of light when it does this. So the light from an atom is quantized to discrete packets of energy. Okay, so that's all the basics of quantum physics. Here are some technical notes which aren't essential to know, but pause the screen now if you're interested in a little bit more mathematical detail. So to round up, in quantum physics objects are described with wave functions, but when we measure them, what we see are particles. So this leads to particle-wave duality and also the measurement problem. And the consequence of these wave functions are the quantum phenomena of superposition, entanglement, quantum tunneling, the Heisenberg uncertainty principle, and energy quantization. So if you understand these things, you've got a good basic understanding of quantum physics. Despite its reputation, I think that quantum mechanics isn't too difficult for most people to get the basics of what's going on. In the past, I've relied on analogies to try and explain it, but here I've just described what's actually going on, which I think might be more helpful.
ഓക്കെ, നമുക്കിനി നമ്മളെ മെയിൻ ടോപ്പിക്കിലേക്ക് പോകാം. നമുക്ക് ഡിറാക് നൊട്ടേഷൻസ് ഒക്കെ നമുക്ക് അടുത്ത വീഡിയോയിൽ നമുക്ക് അത്തരം കാര്യങ്ങൾ ഡിസ്കസ് ചെയ്യാം. ഓക്കെ, താങ്ക് യു.